Chapter 9, Introduction to the T Statistic. The purpose of this video is to walk you through an example of a directional hypothesis test using the information we use to conduct a non-directional two-tailed test for the example pertaining to the amount of time infants spend looking at the attractive face opposed to the unattractive face. So this is example 9.4 from the text. The average amount of time expected if the null were true is 10 seconds, meaning that the infants will spend an equal amount of time looking at the attractive face as they do looking at the unattractive face. So they're studying these faces for 20 seconds. If there's no preference, that 20 seconds will be divided in two with time spent equally on either face. The step one of our hypothesis process indicates that we must state the research and null hypothesis. So the null could be stated in this manner. The null states that infants will spend less than or equal to half the time looking at the attractive face. The notation reads that the mu attractive is less than or equal to 10 seconds. The alternative hypothesis states that infants will spend more than half the time looking at the attractive face. So the notation would read that the research hypothesis indicates that the mu for the attractive face will be greater than 10 seconds. Now, when we're verbalizing and writing the research and null hypothesis, I often recommend that you begin with the alternative or research hypothesis first. The reason for that is you have that direction in your mind. In other words, we're hypothesizing that instead of just saying there's no preference or that there is a preference for the research, now we're saying that the infants are going to spend more time. Again, that word more is indicative of a directional hypothesis. So because you have that at the forefront of your mind, it's easier to verbalize and begin with the alternative hypothesis. So my recommendation is always to write that one first. So infants will spend more than half the time looking at the attractive face. And again, the notation, the greater than, is easy to remember because that's the direction of interest. And then to write the null, you always have to include the opposite direction in terms of greater than or less than, and always include the equal sign. So the null will always have a directional sign and the equal sign, because the null is always saying no difference, no change, which is the same as saying equal. But if it's directional, then it's the opposite sign that you're anticipating. So again, that's my recommendation, that you begin with the alternative or research hypothesis first, because the direction will be something you're thinking about, and then simply do the reverse and include the equal sign for the null hypothesis. Step 2 says that we need to set the critical region. So I'll walk you through the process of doing that for a one-tailed test. So for this example, we've been told to conduct a test with alpha equal to 0.01, which is 1%. We know from the previous information provided, degrees of freedom is equal to 8. Again, our sample size was 9. Degrees of freedom is simply n minus 1, and that gives us 8. And it's important to draw your diagram and set the critical region based on the hypothesis. So if we're anticipating something greater than the mu, again, the mu here is set as 10 seconds, then we're going to focus on the tail to the right. And we're not going to do anything on the left because this is a directional one-tailed test. So we only need one critical t-value, and it will be to the right of the center because we anticipate an increased amount of time spent on the attractive face opposed to the unattractive face. Or I should say in comparison to what we would expect the average to be if there's no preference. Again, this represents mu from null hypothesis, no difference, equal amount of time on both faces. So now let's use our t-table to identify what our critical t is equal to. So again, degrees of freedom is equal to 8. This is now a one-tailed test, so we're going to use this tier, and we set alpha at 0.01, so that's the value. And we're just going to see where these values intersect with one another, and we find that our critical t is equal to, and instead of putting the positive and negative version, we're just going to put the positive version because, again, we're focused on one side of the distribution given the hypothesis stated. So our critical t, again, is 2.896. And again, as we've learned, that if our sample mean converted into a t-value falls in that critical region, we get to reject the null. We reject the idea that they'll spend an equal amount of time or less time on the attractive face, and we get to support the idea that they would spend more time on the attractive face. And now this whole area is representative of failing to reject the null. So that means they spent an equal amount of time or less time on the attractive face. So now to draw these conclusions, we have to engage in step 3, which is to calculate our test statistic, and then step 4 is to draw our conclusion. The test statistic, or t-value, has not changed given what we had calculated in a non-directional test. None of those variables have changed. So here I've cited all the given values. The mu that represents the null, it's 10 seconds, sample size, the sample mean, the standard deviation for the sample, and the estimated standard error. And our t equation is, again, our sample mean minus the population mean divided by the estimated standard error of the mean. We replaced those variables and we came up with a t is equal to 3.00. Now going back to our graph that we had drawn in the previous slide, we have our critical t set at 2.896. And again, in the center here, and I should, I'm going to do something just to be really clear here, as clear as possible. The sample, or the mu in the center is equal to 10. Our sample mean, right, it's converted into a t-value of 3. And our critical t, again, in the center, t would equal 0. Our critical t was set at 2.896, which defines the critical region. And we just calculated our t statistic for the sample mean of 13. And we see that the t-value is going to be to the right of our critical t, so places us in the critical region. And we would equate that to saying that 13, the value of 13 is over here somewhere. Again, there is a value that represents a sample mean that represents the critical region, but we are just going to use the critical t-value to partition the critical region off from the rest of the distribution. And again, since our sample mean of 13 converted into a t-value, again, this is the same as saying a t-value of 3.00 is in the critical region. We know at this point we are happy, right? We're happy we get to reject the null because of the parameters that were set. And that leads us into the next step, which is to draw our conclusions and write our concluding statement. So our concluding statement would be as follows. We reject the null. Results indicate that the infant spent significantly more time looking at the attractive face than would be expected if there were no preference. Or you could state that they spent more time looking at the attractive face than would be expected if the null were true. And then we would include the proper notation. Our t with the degrees of freedom in parentheses is equal to 8. Our t statistic was equal to 3.00. the probability was less than our alpha, 0.01. And now we learn that if you conduct a one-tailed test, you should include that after your probability statement. So one-tailed meaning directional test. And if you had measures of effect, you would include those as well. But again, this statement here is saying that there is less than a 1% chance that we would obtain a sample mean equal to 13 if the null were true. Again, there's less than a 1% chance that we would obtain a sample mean of 13 if the null were true. The null says no preference, or in this case, for the directional hypothesis, they would spend less than half of the time on the attractive face. So this is how we would conclude this type of directional hypothesis test, and pointing out, the way that this differs from a non-directional, or the example that we walked through in previous videos, is simply that the T statistic was different. And if we go back to this slide, the T statistic, was actually smaller than the non-directional test. The non-directional critical T was 2.306, positive or negative. And we've learned that in the past that one-tailed tests or directional tests are easier to pass because the critical regions are set a little closer to the center. They're usually a lesser value when you're using the same alpha level. So that does it for this demonstration of a one-tailed test for a single sample t-test.